and welcome. I'm Jenna Logue. According to the Centers for Disease Control and Prevention, sickle cell disease affects between 90,000 and 100,000 Americans, occurring in 1 out of every 12 blacks or African Americans or Africans or people of sub-Saharan descent. The illness gets its name from the shape of the red blood cells, which can clog arteries. Those sickle cells also die earlier than healthy blood cells, leaving the individual with a shortage of red blood cells needed to carry oxygen to other parts of the body. So how can a physicist help the medical community unravel the mystery of this malady? Dr. Daniel Erenso is a professor of physics at MTSU. His ongoing research, performed totally with undergraduate students, is our subject today. Daniel, welcome.
Thank you.
Thank you for being with us.
Pleasure to be here.
Let's talk first about the technique you use to study the cells under the microscope with what are called laser tweezers. What are laser tweezers and how do you use them?
Yeah, laser tweezers, commonly referred as optical tweezers. It's one of the novel optical devices that have been around for the last 3-4 decades. And it uses lasers. So we take this laser, in particular for our research, we use a specific type of laser called infrared laser, because that's the kind of laser we need to work with the living objects, because some lasers are dangerous, some lasers are good for living cells. So what we do is we take this laser and we send it through different kind of lenses, and we focus it to a very, very, very small size. And if you do that with the lasers, any microscopic objects as small as a single atom or as big as 100 micrometer, which is like 1/100th of the thickness of human hair, you can trap it and you can manipulate it. So that's the basic element of laser tweezers. You have this laser, different kind of lenses, mirrors, and microscope with the microscope objective lens.
And the objective of pinpointing a sickle cell is to not isolate it, but differentiate it from the other cells within the blood?
The use of the laser tweezers is basically if you can grab something at a microscopic level, then and also if you can manipulate it, then it's very useful. So what we do with red blood cells is we get these blood samples, and inside a blood sample you have the red blood cell and the white blood cells and other elements. So we just grab this one red blood cell and we can squeeze it, we can stretch it, and that helps us to understand the mechanical property or the elasticity of these cells.
And how novel is the utilization of the laser tweezers in this area, in sickle cell research? Are you the first person, so far as you know, to have ever done this or to be working with this, conducting research in this area?
No, I am not the first one, but I would say that what we recently discovered in our lab is probably a new thing. In the past, researchers have been able to use laser tweezers, to stretch them or compress them by different means, by attaching small microscopic beads to edges of these cells, and by grabbing this bead on both sides and moving the beads, you can stretch it and you can study the elasticity of these cells. But what we discovered in our lab, to the best of our knowledge, is you can actually trap these cells, and if you apply enough power of the laser, you can actually break the cell membrane. In biological terms, it's referred as lysing. And so what we do is we put this high power laser in the infrared region, which you can't see it with your eyes. That's the kind of laser that you have to use if you are dealing with living organisms, microscopic living organisms. So we observed that if you put these cells at high power, you can basically break the membrane. In a physical term, you can ionize the cell. So when you break the membrane, the different elements inside the cell, since they have charge, then they released from the cell. It's like, a fireball. When it explodes, you see these kind of things coming out.
Everything goes everywhere.
Yes. So it's kind of doing that at a microscopic level. So, the size of these cells is about 6 to 8 micrometer. And you can imagine that that's like 1 over 10 raised to 6 of a meter. 1 micrometer.
Much less than a human hair.
Yeah, much less than. So imagine that you take this such small living cell and then explode it, and imagine that the things that's coming out from this cell, if you are able to know about their electrical properties of each of these individual objects that's coming out of the cell.
And exploding the cell makes it easier to study?
Yes, because basically, for example, in the case of sickle cell patients, the patient has to go through every month what we call hemoglobin quantitation, and that requires opening up these cells. There is a technique called liquid chromatography that's most of the sickle cell centers, for example, Mahari Medical College, to which I'm collaborating with.
In Nashville?
In Nashville, yes, yeah. They have a sickle cell center, and they get blood samples from different parts of the state, and they analyze the amount of these different types of hemoglobin, whether it's a normal one or a sickle one. They use this technique, so that requires opening the cell, but they use different techniques, and that doesn't have the freedom to know all about the elements inside the cell. Our technique, we believe that if you make a live opening of the cell using a laser tweezers, then you can use their electrical properties, and you can add the magnetic interactions to it, and you can literally be able to know the charge amount or the charge property of the individual elements in the cell.
And how does that help the scientist, the biologist, the epidemiologist in studying sickle cell? How does that lead him or her to greater knowledge of, how does knowing about the electrical properties lead him or her to greater knowledge of the disease?
Well, as you know, sickle cell disease, it doesn't have a cure.
Right.
A cure at this stage. There are different kinds of treatments. If you, in the future, for scientists or people in the medical field to develop, these curative therapies, it's really important to know the electrical as well as the magnetic properties of whatever inside that cell. So one of the things that I have been collaborating with Dr. Maria Guinaga, who is the co-director of the Sickle Cell Center at Mahari Medical College, is there is this study by NIH where people who are even in regular treatment, not curative treatment, but in a regular treatment, they use this drug called hydroxyurea in conjunction with a regular blood transfusion, where the patient has to take this blood transfusion of normal red blood cells, I think every 3 months. So this drug has some problems with some patients.
They have a bad reaction to it, side effects?
Not exactly side effects. Well, it has its own side effects, but there are patients who doesn't respond to this drug.
It doesn't work for them?
Yeah, for some. And the study is about 20% of the patients, if I remember that accurately, do not respond to this particular drug. And there is no way of knowing that in advance without the patient being exposed to. So me and Dr. Aguinaga, we actually worked on some grant proposal to use this new technique, which we discovered in our lab, to, if we can apply it in determining whether these patients are responsive to these drugs or not, without the patient being exposed, without the patient taking the drug.
And if you can do that, you can save everybody a lot of time, money, and aggravation,
yes,
including the patient.
Yeah, including the unnecessary side effects. So, so this new technique, we think that it would give us more information, and it could possibly be useful for developing that kind of tools, now, diagnostic tools.
The word breakthrough is used really cavalierly by people who are non-scientists, people who are searching for a big headline. So we do not mean to imply that the work is directly going to be responsible for a cure for sickle cell anemia, but it could be a very crucial diagnostic tool in helping scientists as they continue to perform research. It'll be a step along the way toward trying to unravel the mystery of sickle cell anemia.
Yeah, you can say that. Well, it's I wouldn't say it's a breakthrough, but we think that this tool can be potentially be useful for that purpose. Yeah, this new tool we to the best of our knowledge, we discovered in our lab.
Is there anything dangerous about using the laser tweezers? Do you have to put on goggles to protect your eyes?
Yeah, absolutely. Because one thing as I mentioned at the beginning, if you work with the living cell, you have to use lasers which are in the infrared region. This is, I don't know, people.
It's a high frequency or a high band on the spectrum.
It's a high wavelength in terms of wavelengths, but high wavelength lasers are not harmful at the molecular level. But if it is too high, if it's too high power, then it's going to be dangerous. The infrared laser we use, you cannot see it. A laser pointer, a red laser pointer, you can see it, right? That's in the visible spectrum. All this light, we can see it.
We can't see ultraviolet rays either, but we all know that they can cause sun damage to the skin.
Yes, so that's at the molecular level. Those lasers, they have a shorter wavelength. If it is a shorter wavelength, what we call in physics photons, which is particle of light, the energy is going to be high if it's a shorter wavelength. If it's a longer wavelength, the energy per particle of light is not that high. So that's why we use the infrared laser. You can preserve the integrity of the cell at the same time, if you don't put too much power, of course.
Okay, you have to know how much power to apply.
Yes.
You can see how Dr. Erenso is good at describing these very complicated scientific issues for a lay audience, because he teaches undergraduates. MTSU does not have a master's or PhD program in physics. So all of the students with whom Dr. Erenso works in the classroom and in the lab are undergraduates.
Exactly.
Out of high school or prep school, and they will graduate with a bachelor's, a BS, in physics when they leave you. Talk about how these undergraduates interact with you and how they help you and how you help them. You must recruit, or your department must recruit, the best and the brightest, right? Because the typical undergraduate comes here as a freshman and is still just trying to fumble his or her way around campus, trying to figure out, you know, where to live, what to do, where to go to eat, and pay their fees, and this and that and the other thing. But you have students performing very high quality work with you, in addition to the usual pressure of grades and becoming acclimated to the university environment and so forth.
Yeah, our department is, I would say, a lucky department because we get really the brightest students. And in regard to that, our department chair, Dr. Ron Henderson, he has been doing a really fabulous job. We put a big effort in recruiting the best students from the Middle Tennessee area. And, you know, students, they are invited to the department and they come and they visit our research lab. It's not only me, but there are also other faculties who do really outstanding research. And you know, these students, when they see this research, they get excited. And so we get a really good student as a physics major, but I'm not limited only to physics major. You know, this is kind of a biomedical interdisciplinary research. So, you know, I teach introductory physics 2, which is electricity and magnetism. So that course is required by most of pre-med students or pre-health students. And, you know, I see in the classroom these students and, you know, I approach them and I talk to them, you know, what kind of research that I do, and I ask them if they are interested to come and visit the lab. So they come, and over the years I have worked with quite a few students who are not physics major as well.
For all intents and purposes, these undergraduates who are working with you are doing graduate level work, are they not, qualitatively? Oh
yeah, they do really, really outstanding work, you know, this is not only in my research lab, but in general in the department. Students, they publish, you know, in peer-reviewed journals on the research they do. Which is something that is usually not done by undergraduates in a lot of disciplines. Oh, that's very, very rare. Yeah, you don't see that, you know, let alone publishing independent research. This is, you know, independent research. The students, they do the research, they go to the lab, they do the things, they write the paper, and we help them in doing that. And, you know, these papers got published in peer-reviewed major journals. And as a matter of fact, as we speak, as we tape, of course this is taped, there are no secrets in television. You're an intelligent audience, you know that. As a matter of fact, we are toward the end of the semester, and even though classes have already ended for the fall 2015 semester, you have students who are voluntarily in the lab right now working on things just because they want to. Exactly, yeah. You know, I really love working with undergraduates rather than graduates, maybe because our department doesn't have a graduate program. But, you know, working with undergraduates, what really makes it good and enjoyable is you work with these students who are highly motivated. And for me, you know, as for undergraduate students, what I really want them is to get the exposure, to get the experience, what you can do with physics. It's not just only problem solving, or just memorizing some formulas. Is it can go to any kind of research. So I want them to give this experience, and the different research areas that's going on in the department, it really motivates them, and they are very excited about it. And some students, they spend even the summer without being getting any assistant, just for the love of the research.
Do most of your undergraduates who get their bachelor's go on to graduate school?
Oh yeah. They go to grad school. They go to the research, different research laboratories. In the past, I have quite few students who have been accepted with different science research lab at Vanderbilt universities, and those science, they call me and ask me about those students, and I hear also after they left that and go to grad school, I hear a really good positive comments about those students.
And the reputation of the department spreads as a result, and other students find out about it.
Yeah.
Are you still working with Dr. Ying Gao of the MTSU Department of Biology?
Oh yeah. I am still working with Dr. Ying Gao, and actually she's very, very collaborative and very helpful, and she is in the Center for Tennessee, Tennessee Center for Biomedical Medicine Research, and they are doing really a great job there on this traditional Chinese medicine, and it's actually helped me to add a new dimension to my research. I have been working mostly on sickle cell, human red blood cell, and because of the department, because of her work, I am able to extend my research into cancer research.
Now, what you're doing is taking an herb that the Chinese have used for centuries and attempting to determine through scientific method and empirical data its efficiency or lack thereof. You will determine whether the information that you get from the Chinese anecdotally has a basis in scientific fact.
Yes, yeah. Well, they do that also from the biological side, but what really makes this the traditional Chinese medicine more interesting is because studies have shown that if you treat cancer with this traditional herbal medicine, it can also increase the sensitivity of these tumor cells to radiation. In cancer treatment, it's not only radiation or it's not only chemo.
Sometimes they combine.
Yeah, they combine, which is referred as radiochemotherapy, sometimes may have more effect. So if you treat a tumor with a radiation, then if it's just only radiation, it might need more dosage. But if you add chemo to it, you probably the amount of radiation you need is not going to be that high. And this Chinese herbal medicine have shown some indications that if you treat the cell with this Chinese traditional medicine, the amount of radiation that you need, it may not be that high. So what we are trying to do in our lab is to test that. So yeah, Dr. Gao, she treats these different kind of cell lines, breast cancer cell, lung cancer cell, with these different kinds of Chinese traditional medicine, and we take those samples and we put in our laser tweezer, and we see how much radiation, for example, you need to kill those treated cells in comparison to those cancer cells that are not treated with this traditional medicine.
And if the research ultimately determines that the patient can use less radiation, it will be a less odious experience for the patient, because neither radiation nor chemotherapy is a terribly pleasant experience. And I'm sure patients, by and large, would rather undergo less radiation if they can.
Yeah, that's the idea. That's the goal.
What sort of prospects do you have for obtaining grants to help fund further research?
Well, I have been trying. I wouldn't deny that.
Applying for a grant, it takes a whole different vocabulary and the use of very specific words to attract the attention of the people with the money.
Yeah. And we have to know that we work with undergraduate students only, and that has its positive, and sometimes it has with the reviewers, if you come up even with a really great idea, they may think that, how could you accomplish this goal just only with working with undergrad student?
They don't think it can be done.
I think they probably think that, but we have been trying to with Dr. Gao, and also with Dr. Maria Genaga from Harry Medical College in the past. We jointly submitted grants to NIH, and we haven't succeeded yet, but we get good review sometimes, so we will keep on trying.
By all means, please do keep on trying, because this type of research is ultimately, especially the interdisciplinary aspect of it, potentially a boon to millions of people. And the use of physics in helping the medical specialist further their own research is extraordinarily valuable in and of itself, and one of those little behind-the-scenes aspects of science that we don't often get to know about. So thank you for letting us peek behind the curtain.
Thank you.
Thank you, Dr. Erenso.
Thank you.
And thank you for watching.